Let's get started. And as you already know, today we're going to be talking about how to reduce hallucinations in LLMs, and we're going to specifically talk about the strategies for the monitoring and mitigation of hallucinations in large language models. Let's get started with kind of the why we should be talking about it, or why me. So first of all, we're an open source company that focuses on classical ML monitoring, so anything that has to do with monitoring the predictive models. Mostly on tabular data, so anything like churn modeling, etc. We do monitoring there, but we're also right now building a hallucination detection tool that's going to be available in the coming months. And as part of that, we also did our research. We read and evaluated hundreds of papers that deal with detection of hallucinations in large language models. And basically, that's the reason why I'm now talking about it. And the results of that research will be presented at the end. So please stick with us until the end, and you'll see basically what are the best techniques that we evaluated on real-life language data sets and real-life prompts. So let's get started with the agenda. First, we're going to talk about what is actually LLM monitoring. So why should we monitor LLMs and how you do it? And then we're going to talk about 4 different approaches, 4 different branches or groups of strategies for LLM monitoring. The first one is going to be based on LLMs, where we're going to use LLMs to monitor LLMs, and we're going to focus on the consistency of the answer. The second one, we're going to be directly using an LLM to evaluate whether the answer to a prompt is likely to be hallucinated. Then we have 2 groups where we're going to focus on uncertainty quantification. And the first one there, we're going to focus just on the output uncertainty quantification in kind of a simpler way, which is a great benchmark and baseline for hallucination detection. And then we're going to focus on slightly more advanced approach. We're going to talk about semantic uncertainty and semantic meaning of the answers, and how to incorporate that in our uncertainty quantification for detecting hallucinations. And then at the end, we're going to show experiment results of few of these approaches, few of the papers that we implemented, and you're going to see what basically works best and how to evaluate even when hallucination detection succeeds. So let's start with the first part, which is what is LLM monitoring? There's basically 3 different types of LLM monitoring. The first one is the infrastructure, where we're going to be monitoring the uptime, the latency, all these kind of infrastructure metrics to make sure that the LLM is actually online and it's giving answers to the users in timely fashion. The second one is monitoring the usage. So we're going to be monitoring things like conversation length. We're going to be potentially monitoring the sentiment, whether the users respond positively to the answers given or negatively. And we're going to be potentially monitoring the topics to see whether the LLM is used in line with its intended use. It's kind of an obvious thing. So imagine that you have an LLM that you're using as a chatbot for your, let's say, car manufacturer or a car dealership, and you want to make sure that most of the topic here revolves around cars, and that people don't use it, for example, to do their maths homework, which is something that we've already seen quite a lot. And then the third part, which is exactly what we're going to be focusing on, is monitoring LLMs to detect hallucinations. So here we're going to be trying to figure out what are the potentially incorrect, incomplete, or vague answers, and we're going to be flagging those to make sure that these are either not displayed to the end user or displayed with a certain warning that we know that this answer is incomplete and the user should be wary of actually acting based on the output of an LLM. So, as I mentioned, this is the focus of what we do now, what we're focusing on now in terms of LLM monitoring. Now, in terms of what we actually want to evaluate for hallucination detection, we can look at it from 4 different perspectives. We can look at the kind of the full answer when we have a prompt, for example, how to detect hallucinations in an LLM, and we get an answer from an LLM, and we can just evaluate whether the entire answer contains any hallucinations, vague answers, incomplete answer, etc. That's the first approach. It allows us to really kind of in one-to-one fashion say whether the answer was correct or not. So in that terms, it's very useful. However, it sometimes might be very hard to do, and there might be some hallucinations in some paragraphs that don't really matter, and the answer is still mostly correct. So if we monitor the full answers in terms of hallucinations, we might be dealing with a bit more false positives than normal. Then we can look at the paragraph level when we will just look at paragraph per paragraph, whether there is some hallucination in a given paragraph. That already gives us a bit more detail about where the hallucination might lie. But of course, then we're trading the fact that one paragraph might be correct, the other one can be completely off. And for that, we'll need to really have some kind of summary method for the entire answer built off of separate paragraphs. And this is basically one of the kind of typical ways of doing monitoring right now for LLMs. And the last one, I think right now, I would say the standard way of monitoring LLMs for hallucinations is looking at each sentence and evaluating whether this sentence is actually correct, complete, and unambiguous. So here we're going to be looking at each sentence separately and providing some kind of score, some kind of measure of whether this sentence contains hallucinations. And last option, which is not very meaningful, although technically we could do it, is we could evaluate whether each token is actually correct. This is not very meaningful in terms of language, but just for the sake of completeness, I added here as well. So we're going to be mostly focusing on monitoring per paragraph and per sentence, with the bigger focus on monitoring per sentence. Now, we already know what is LLM monitoring and what are the things that we can actually monitor. Now let's start talking about the taxonomy for the algorithm detection, for the hallucination detection types. What are the different kinds of algorithms that we can use to detect hallucinations in LLMs? And basically, we have two main families here. So the first one is LLM-based, and we're going to call another LLM or another instance of the same LLM, and we're going to measure either the consistency of the original answer, or we're going to directly evaluate the answer using LLM as kind of this external evaluator instead of like a human. Then the second one is we're going to try to get some kind of notion of uncertainty from the LLM directly, and instead of calling another LLM, we're going to use that notion of uncertainty to say something about the quality of the output. So if an LLM is very uncertain in the answer that it provided to the prompt, we can say that this answer is likely hallucinated, or that we cannot be sure that this answer is actually correct at least. And here we can again focus on two things, whether directly just looking at the output that was produced, or potentially looking at all potential outputs and trying to find whether semantically the algorithm is actually sure of what should be the answer from the meaning perspective and not just the words. This sounds very vague for sure, and I will explain in detail later on once we get there what this actually means. So now just bear with me and let's focus on the LLM-based hallucination detection. We're going to be starting with the consistency approach when we try to measure whether the LLM outputs, LLM answers are consistent across different seeds or different temperatures. So how does it work? Let's say we have the same prompt as always, which is how to detect hallucinations in an LLM. And then our LLM, let's say we query it 3 times with a different seed, and it's going to give us 3 different answers. The answers are generally very, very similar. They're not exactly the same because of the random seed. If our temperature is higher than 0, then we're going to get different answers. But we see that generally speaking, these answers, just looking at it as a person, you could say that there's different words used. Maybe the structure of a sentence is very, very slightly different, but generally it's quite similar. And based on that, us as humans, you could say that, yeah, these are basically very similar answers. The answer to that question is consistent. So we're going to put some kind of high value, let's say our similarity measures between 0 and 1. We're putting some high value, let's say 0.875, that this is similar. This is the overarching idea, intuition of what we want to get with our consistency-based hallucination detection. How does it actually work? Well, so first of all, it will just call an LLM multiple times with a different seed, for example, and then we'll measure the consistency of the answer. The question, of course, is how do we get different answers and how do we measure the consistency? Before we go there, quick list of pros and cons. The pros are quite nice. The first one is that we don't really require access to probabilities. So if we want to work with an LLM that doesn't output probabilities directly, token probabilities, such as GPT-4, we can use it. So that's a huge deal. Unfortunately, it does require multiple calls to the same LLM, which might get quite costly. For example, again, we don't want to call GPT-4 4 or 5 times every time we try to evaluate whether the answer is consistent or not, just for the case of monitoring, because then monitoring de facto costs 3 times more than actually using an LLM, which might be needed and acceptable in really critical applications, but it's generally not something that's desired. But we pay quite a lot for that, but we get good performance. And generally speaking, this kind of hallucination detection tends to perform quite well. Now, let's answer our 2 main questions we had. The first one is, how do we even get different answers if we ask the exact same question? So first thing we can do is we can just change the seed. This is the obvious way of doing it, and most papers just talk about changing the seed, getting different answer, and measuring consistency. We could also adjust the temperature. Of course, that changes a bit more than just randomness, because then we'll, if we increase the temperature, we're more likely to get random answers. So it's not as good as changing the seed, but it's something that has also been tried, mostly with bad outcomes. And then the last thing is use an LLM to paraphrase the prompt and then use that as a new prompt. It's also an option, but it means yet another LLM call, increasing the costs further. So generally speaking, we want to stick with just changing the seed and seeing whether the answers are similar to each other. Now, how do we actually measure this similarity? How do we measure consistency? One option is that we give these 3 answers and we tell LLM, evaluate the consistency or similarity of these answers on scale 0 to 1. This surprisingly works. And I know it's calling LLM multiple times and using it as an oracle, and it basically sounds like magic, but in reality, it works quite well. Another option is to use simple cosine similarity. We embed all 3 answers and we measure the cosine similarity on sentence level between them. Very standard practice, and it works quite well. The last one is using BERT. So instead of having an LLM call, we can use a simpler language model to measure the similarity. Just an example paper that I think is probably the most interesting from this family of ways of measuring the consistency or detecting hallucinations via consistency. And it's SelfCheckGPT. You can check it out here. We'll be also sending the presentation, so you can just click on the link once you get the presentation later on. So that was the consistency, LLM-based hallucination detection. Now we're going to be moving to the second part, which is LLM-based hallucination detection using directly answer evaluation with another LLM. So let's start with an example again. So we have the same prompt, the same answer. We're going to just feed it to another LLM. We're going to prompt engineer basically how it should answer. So we're going to put the prompt, we're going to put the answer, and we're going to ask LLM, evaluating it on scale 0 to 1 across correctness, completeness, and grammar. Give the score, evaluating that answer to that prompt. Then we attach the prompt and the answer. This is literally how it works. And then LLM outputs what is the correctness. Of course, if we add more examples, etc., it's going to work better. But I don't want to go too much into detail here. It's more of an overview of the method. Now, to go a tiny bit into detail here, how does it work? We're going to use another LLM already, as I mentioned, to evaluate the quality of the answer by giving it the prompt, the answer, and the metrics that we want to evaluate. The main con of that, of course, as I already mentioned, it requires a single additional LLM call, so it's already cheaper than the first method, but we need to have a very complex, probably well-tested additional prompt to make sure that the metrics we get are actually meaningful and they're on the level of the meaning is not only generally meaningful, but the meaning is the meaning we want. And again, we don't require access to probabilities, so we can work with the newest OpenAI models that don't output probabilities. We can include any kind of custom metric we want, not just whether there is hallucination or not, but whether the answer is grammatically correct, whether it's precise, whether it's polite, basically any kind of metric we want. And generally speaking, based on the papers I've read, so according to current state of the art, this is the best, if not the best, ways to detect hallucinations. It's quite interesting again. So quite a lot of good pros and just one con that it does require a lot of prompt engineering with additional LLM code. There's of course one big question, which is what LLM do we actually use to evaluate the LLM question? And here we basically have three options. We can either use a simple LLM, and that's the one we're using. Let's say we're using a 70 billion parameters model. We can go to a smaller model of the same family, or even just completely different smaller model that's going to be cheaper. But of course, we need to then double or triple check that this simpler LLM is actually able to accurately evaluate the hallucinations of a more complex model, which in principle is possible, but it's not always as performant as using the same LLM, which is the second option, when we just the exact same LLM that we're using for our use case, and we just always send one additional single call with this prompt, the answer, and the additional prompt that tells the LLM what metrics to use. This is very simple. It doesn't require any additional engineering, basically, apart from adding the additional call. And into the decent solution. And then the last option is, of course, to use the best LLM available, whatever is at the current top of the leaderboards. But it's expensive, and if we're using that for evaluation, we probably should use it instead to actually answer our question, because then we're less likely to get a hallucinated answer. Example paper here is LLM-eval. Again, the name is not very creative, and you can click on the archive link to go through the details of the implementation after the webinar once you get the presentation. So these were the LLM-based hallucination detection methods. And now we're going to go to the second part, which is the uncertainty-based hallucination detection methods, starting with the first one, which is the output uncertainty quantification. Yes, exactly. And again, as always, we're going to start with an example. How are we going to do it this way? This time is completely different. So instead of just getting the answer, we also need to get the probability of getting that answer. Token probability is called. For each of the tokens, so each of the words that we have, or symbols, in the LLM answer. So that's what we get. So for every word, we also get a number. And then we're going to use those numbers to quantify the uncertainty of the model. So we're going to get some kind of confidence score, say 0.12 here. And that's the idea. Now let's talk about what it actually is, what are the pros and what are the cons. And the key questions we have, and of course, one of the key questions is, what do we do with those numbers? How do we actually use those numbers to get one number at the end that will tell us whether the sentence or the paragraph is hallucinated or not? So the details. First of all, what does it do? It measures how certain LLM is of its own answer using the token probabilities. So we are, again, de facto using the LLM, but not by calling it again, but by just taking additional output that it, generally speaking, always outputs, which is the token probabilities, and using that as a measure of its own confidence in the answer. And the rationale behind it is that, generally speaking, it's another paper, LLMs know what they don't know, which means that they can reasonably well quantify their own uncertainty. And we're going to be leveraging that fact to try to come up with some way to detect hallucinations. What are the pros and cons of that approach? Well, the first one is now we do require access to chosen token probabilities, which means that more or less we're stuck with open source LLMs, which of course getting stronger and stronger every day, but they have not fully caught up across everything, at least, to the closed source LLMs. And they require also different engineering choices and decisions. And as long as our organization is already using open source LLMs, that's of course fine. But if it's not, then this is going to be a significant obstacle. Good thing though is that it does not require additional LLM calls, which means that especially at scale for use cases that we need to operate at large scale, we will be saving quite a lot of money, because we're at least cutting our LLM calls in half compared to using the LLM evaluation approach, because we don't need to do this one additional call for every call that we get as part of the use case. Which means, of course, that it's very cheap to run, and our performance is not stellar, as we'll see in the results, but it's still quite good compared to the LLM-eval. It doesn't match it, but we still get reasonably meaningful detection of hallucinations. And example paper here, which is kind of a baseline paper, I would say, called Looking for a Needle in a Haystack, from, I would say, I think more than a year ago now. It's also available, and as always, you can view it later. Now, let's talk about the details of the actual algorithm. The first question is, what should be the uncertainty measure? So we get all these numbers, one number probability for every token, and how do we use it? Basically, another way to frame that question is, what is the probability of the hallucination given those numbers, given the sentence we have, and token probabilities? And we can look at it from kind of at least 3 different perspectives. These are the perspectives that are explored in the paper, but I'm sure you could come up with way more. Actually, mostly 2 of them are explored in the paper. I added the geometric mean token probability for a reason I explain in a second. But these are the 3 main reasons or ways to quantify the uncertainty. First, we can just look at all the tokens and take the average token probability. From kind of the meaning perspective, what we want is that on average, the LLM is quite confident in its answer. So even if it's not very confident in one of the tokens, probably the answer is still fine. This is one way of looking at it. Another way of looking at it is that these probabilities are in some way multiplicative, because we start with the first one, then we get the next one, then we get the next one, etc., etc. So maybe kind of intuitively, it makes more sense to use a geometric mean here instead of just a normal average or normal mean, which kind of makes sense because we want to the idea that if we have one very, very low probability token, we want to take that into account more, because this one probability token might be actually very important. It might be the key fact or maybe key name that we're looking for, and it might be wrong. So this is something that is potentially slightly better than the average token probability. And then the last part is, generally speaking, if you say a sentence where every single word is correct except one word, generally speaking, I use generally speaking a lot, you could say that the entire sentence is still false, even if just one word is wrong. If you say the capital of France is Rome, this is a hallucinated sentence, even though every single word in that sentence, except the last one, is fully correct, very confident. So maybe we should then just focus on the minimum token probability. And this is the last option, and this is the option that, according to at least our experiment, tends to perform best. So now that was kind of simple uncertainty quantification just based on the output. But let's talk now about slightly more advanced idea, where we're going to be working with the semantic uncertainty quantification. And that generally means that we're not going to be focusing only on the words, but on the certainty of the algorithm, of the meaning behind the word, or behind the answers that it gives. Let's talk about how it works. So what we're going to do is we're going to have a prompt. And then instead of looking just at the answer it's given, we're going to look at all the possible answers that can be created using top 3 tokens for each answer. So maybe the first answer, the most likely answer it would give is Paris is the capital of France. Another answer that the LLM could give that's still quite likely is the capital of Paris, the capital of France is Paris. And maybe another option is LLM would answer capital of Paris is France, was keeping the for some reason. And then we're going to try to use this kind of tree of possible answers to kind of quantify the uncertainty. And what is the rationale behind using the entire tree instead of just a single answer? Well, the problem with looking at the single answer is that maybe the model was very, very uncertain between answer 1 and answer 2. What is the capital of France? Paris versus the capital city of France is Paris. Both answers are correct, but if we just focus on the simple uncertainty quantification, and the algorithm was very uncertain between answer 1 and answer 2, we would get the impression that the model is actually uncertain of its answer, so it's likely to be hallucinating, which is not the case at all. The model is actually very confident in the answer is sparse, it's just not sure how to phrase it. So that's kind of the part of the rationale why we really care about semantic equivalency and not just equivalent in terms of, and not just uncertainty in terms of just answers. And then the second part of why it's important is compare answer 1 and answer 3. Answer 1 and answer 3, if we evaluate it via, let's say, mean token probability or geometric mean token probability, would be quite high because the capital city of France, they will probably be very high certainty tokens. And if you look at also the similarity between answer 1 and answer 3, so let's use the consistency approach, we would also see that the answer 1 and answer 3 are generally speaking very, very similar. But of course, from our perspective as humans, the answer 1 is correct, answer 3 is completely incorrect. It's just factually wrong, even though it looks very similar from the grammar perspective. That's why we care about semantic meaning. Now, in terms of the details, how it actually works, we're going to calculate the probability of getting the answer that we actually got or semantically equivalent answer. Just quick reminder, semantically equivalent answer is an answer that for us humans is basically the same, and the only difference is phrasing. So answer 1 and answer 2 are semantically equivalent, answer 1 and answer 3 are not. And we're gonna, in a second, discuss how we actually do it. Now let's talk about pros and cons. So first of all, we require access not only to the chosen token probabilities, but all token probabilities. Because we need to construct this decision tree that I shown here, where we look at all the possible paths that the answer could take, it means that it's generally quite expensive to run, but at least we don't require additional LLM runs. And it does incorporate, and this is really unique among, I think, most of the approaches here, it incorporates the full semantic meaning of words, sentences, and paragraphs. So we're really looking at it from the language perspective and not just kind of single word perspective. And it does give good performance, of course, because of that. And paper, as always, added at the bottom of the slide. Now, the first question we want to have is, when do we stop? Generally speaking, LLMs can generate vastly different answers, especially if we start looking at very improbable answers. So what we want to do is we're gonna keep on creating this tree, but not until we get to probability of 1 and we get all the possible answers, but until we get certain amount of probability mass of what the LLM could generate. A heuristic is going for 90% of that, but of course with something that we'll have to adjust based on the length of the answer and the amount of compute we have. And keep in mind that this is really exponential increase, because for every additional token in the answer, we're multiplying the possible number of trees by however many different outputs we allow. So that's really quite a lot. And this is what we get. Now, second question we might have about it is, what is semantically equivalent? We understand it as humans, but how we can actually measure it? And the answer is quite similar to the one of the previous approaches, which is we either ask an LLM and say, compare these two questions, are they semantically equivalent, yes or no? And second one is, again, using the cosine distance in the embedding space. So these are very simple, similar approaches to the ones we had with the consistency. We want to measure similarity in some way. Here we're more worried or more concerned about equivalency, not just similarity. So we'll phrase it slightly differently when we ask an LLM. And that is really it when it comes to the overview of the methods. Now let's quickly look at small subsection of the results of our research, and one of the things that we'll put later on as content, as blogs, as videos potentially, and then we'll put it in our hallucination detection toolset. So what we were doing here, first of all, the problem setup. What we wanted to do is we looked at the sentences we evaluated what is the actual ground truth of the sentences, so whether the sentences were correct, whether they were complete, whether they were informative, and the average of those. So that was human evaluators. We didn't do this. Most of it was not ourselves. We did a bit of labeling ourselves, but most of it was already pre-labeled data sets. And then we are measuring the correlation, whether it's Spearman or Pearson correlation, which is the standard across different literature on hallucination detection of the automated hallucination detection algorithms. So here what you see is the sentence ground truth. So how correct was that answer to a given prompt, and what was the evaluation of an LLM. So here we're using the LLM-eval approach. The second approach I described when we use LLM directly to evaluate the correctness of an answer versus the actual ground truth. And we see that the correlation is hovering around 0.4 to 0.5, evaluated with Pearson correlation, which means that it does correlate with human evaluators, but it's not a perfect correlation. So it's useful, but it's not a complete answer. The same with relevance. And interestingly, if we look at the average, it has slightly higher correlation than any of the separate parts. But this is something that we can already use, and we'll be able to catch quite a lot of hallucinations, but not all of them. Now, just same kind of approach in terms of evaluating and setting the problem, but this time we're using the sentence level probabilities. So we're using the simple approach of looking at the uncertainty, and here uncertainty is just approximated or proxied with sentence level probabilities. So for every sentence that the algorithm outputs, we're looking at the minimum token probability, and we correlate that with the sentence ground truth. And we see that correlations are generally a bit lower, but there's still positive correlation between that and the actual ground truth that human evaluators give to an answer. So it's still useful, and it's a much faster, much simpler benchmark or baseline. And then one interesting result we got is that the correlation between the actual LLM evaluation and the answers that we get from token uncertainties are basically not correlated with each other at all, or very, very weakly, which means that using both of these approaches at the same time might actually yield better results than using just one of them. And we can have this kind of bugging approach or voting approach when we use both of them at the same time to evaluate whether a model is hallucinating, and that might be the best solution. But we're still doing research there. And that is really it. So now, just to summarize, what we've learned here today is that hallucination can actually be quite reliably detected and reduced, because if we know the hallucination is there, we can mark it as hallucination, and we can ask LLM again to answer in a different way, or say this answer is incorrect, take that into account when you correct your answer. With the current technology, with the current approaches we have now. And then the second main point is that there are two efficient solutions. What we showed here, basically two most promising solutions, is that we can, if we have access to probabilities, we can use simple uncertainty quantification. It's very cheap, it works quite well, and it's really good kind of a stopgap solution that you can implement very fast. And this is going to be one of our kind of flagship ideas. This is something that can be done really fast, really quickly, and directly embedded in the LLM interface. Then the second approach is answer evaluation with an LLM. So calling another LLM one more time gives basically the best results, and we don't need to have access to probabilities, but we do need to call an LLM another time. And now this is really it. So thanks for listening. If you want to get in touch, if you want to talk about LLM monitoring, if you're interested in the solution we're developing, reach out to me via LinkedIn. And yeah, I'll be very happy to talk, bounce some ideas, show what we got a bit more than I showed here, and hopefully we can figure out how to reduce hallucinations. So thanks a lot, and now I'll be taking any questions you might have. Let me just move things around a bit. In the meantime, are there any questions from the chat? I don't see anything. So the first question I see from Avinash is RAG as evaluation metric. I'm not sure if that is a question or is that just a statement? Here right now is not focusing really on the RAG approaches, so I'm not sure what to talk about it. Another one we got from anonymous attendee is, do uncertainty probability estimate only work on open source models? They work on any models where you can have access to uncertainty, to token probabilities, which excludes current OpenAI models. Older OpenAI models still output access token probabilities. Basically, as long as you have token probabilities, you can use the uncertainty probability estimates. Yeah, I guess I'm supposed to click answer live here. So, a second. Let me do this. No. That is not what I wanted to do. Okay, another question. I won't be able to, unfortunately, do much here. We didn't talk about much about RAG or chunking to reduce hallucinations. Indeed, that is something that we're working on, but just in terms of reducing the scope of the talk and not taking a full 2 hours. We didn't manage to talk about it. I'm very happy to talk with you about it, Kevin. We are doing a bit more research about specific evaluating the hallucination with RAG systems where we have access to some kind of database. And yes, I'm happy to talk about it more. Unfortunately, we didn't have time to do it today. I think these are all the questions, at least the questions I see. If you can help me a bit.
Yes.